Hello everybody, welcome into another lesson. So today we are going to talk about complex numbers. So we're going to start at the bottom of this number tree. Everyone should definitely be familiar with natural numbers, which are just your counting numbers like 1, 2, 3, 4, 5, and so on. And then you have natural numbers that are a subset of the whole numbers, which are all your natural numbers plus 0. So you have 0 included in that, which the whole numbers are a subset of the integers, which are both positive and negative whole numbers. Then integers are subsets of the rational numbers, which rational numbers contain everything below plus fractions or decimals that can be expressed as fractions. And then off to the side on its own, you have irrational numbers such as pi, such as e, or non-terminating, non-repeating decimals. Together, the rational and irrational numbers make up the set of real numbers. Now, we get to talk about imaginary numbers. You have the square root of -1 equals I. When we say imaginary numbers, it's not that it's in our imagination, that they don't exist. They very much exist. It's just the premise of this is there's no real number you could square, raise to the second power, and get a negative number. It never happens in a set of real numbers. But in imaginary numbers, it does. And why do imaginary numbers matter, you may be wondering? If they're imaginary, why even talk about them? Well, they are very useful in fields of engineering or especially in electrical fields. They explain for changes in electrical fields and electrical currents and quantum physics and all kinds of other areas like that. They come into play all the time. And imaginary numbers can have implications in the real number system. Together, the real numbers and the imaginary numbers make up the set of complex numbers. So when we say the complex numbers, we're referring to both the reals and the imaginaries together. So, and if I can pull it up, I want to show you something really cool that you can do with imaginary numbers. So let me see here. If I bring this up, here we go. Let me just temporarily cut out my camera real quick. You have what's called there the Mandelbrot set. The Mandelbrot set is something that is graphed by using imaginary numbers. So that is a really cool application of imaginary numbers. All right, let me get back to where I was. Let me cut that out. No, there we go. All right. So that's a really cool application of it. Now, let's talk more about imaginary numbers. So, since imaginary numbers, you have the square root of -1 equals I, you can add and subtract these numbers very much like you would adding or subtracting a radical, or you can actually treat it like a variable, because when you add or subtract radicals, you treat them like variables. So let's do some examples of that here. So let's say you're asked to find the complex number in standard form. So you're given 5 plus the square root of -16. So you have 5 plus the square root of -16. Well, isn't it true then that this would break down into 5 plus the square root of -1 times the square root of 16? Now, what is the square root of -1? That's I. What's the square root of 16? That's 4. So this would be the same as 5 plus 4i. That's how you would write this in standard form. The standard form of a complex number is considered a plus bi, where that a is your real number and that b is your coefficient of the imaginary number. So that 5 plus 4i is considered written in standard form. All right. Let's do another one. Let's say we have 2 minus the square root of negative 9. So we got 2 minus the square root of negative 9. So we can definitely simplify the square root of negative 9. You'll have 2 minus, now the square root of negative 9, that breaks down into the square root of negative 1 times the square root of 9, which would just give you 2 minus 3i. So that's how you would write this in standard form. This 2 minus the square root of negative 9 would turn into 2 minus 3i. Alright, now let's say you just had negative 6. You just have the number negative 6. There's no imaginary term. There's nothing you can do with it. It's already in standard form. You could say plus 0i, but 0 times anything is 0. So you could just leave it as negative 6. It's in standard form. Alright. Let's say you had 8i. Let's say you just have 8i by itself. Formally, in the complex number system, this would be 0 plus 8i, but 0 plus anything is that anything. So this 8i is already in standard form. You don't need to do anything with it. So if you either just have an imaginary number by itself or a real number by itself, you can leave it as is. It's when you have the two together, a complex number, that's where you have to worry about standard form. Alright. Now, i's also have cycles. So, we're going to talk about the cycles of I. So, let's say you have I to the 0. Well, anything to the 0 except for 0 is 1. So I to the 0 will give you positive 1. Now, I to the first, that is literally the same as I, which would just be the square root of negative 1. Okay, so what about I squared? What would I squared be? So that would end up being the square root of negative 1 raised to the second power. Well, that square root, we could think of that negative 1 being to the 1/2 power. You raise that to the second power, you're just going to get negative 1 to the first power. So I squared actually equals negative 1. People make the mistake of thinking you can take the square root of negative 1, multiply it by the square root of negative 1, and that you'll end up getting the square root of positive 1, which would give you 1. That's false. Let's explain the square root deal even, okay? Let's explain that square root deal. So, the square root of negative 1, of course, would equal that negative 1 to the 1/2 power, right? So, let's say I take that negative 1 to the 1/2 power times negative 1 to the 1/2 power. Well, if you have the same base, you're multiplying by the same base the different exponents, you just add the exponents. This would be the same as negative 1 to the 2/2, which would just be negative 1. So that's why I squared actually equals negative 1. Alright. Let's do I to the third. So I to the third, that's going to be, of course, I squared times I to the first, or just simply I. Well, I squared is negative 1, so you take negative 1 times I, you just get negative I. So I to the third just equals negative I. Now I to the fourth. If you have I to the fourth, that's just the same as I squared times I squared, which is the same thing as negative 1 times negative 1, which would give you positive 1. So it's important to know the very first 4 i's, the cycles of I. I to the fourth gives you positive 1. So I to the 0 is 1 because anything to the 0 power except for 0 itself is 1. I to the first is just that, it's I. I to the second gives you negative 1. I to the third is negative I. And then I to the fourth is positive 1. Now, what if we decided to do I to the fifth? Once you get above 4, what you have to do is you have to take that 5, you take whatever number that is, so take 5, divide it by 4, what do you get? You would get 1 with a remainder of 1, right? You would end up getting 1 and 1/4. We know it goes that 5 goes into, or 4 goes into 5 one time, but you have a remainder of 1. This piece here, this remainder of 1, it treats like an I to the first, which would just give you I. So let's say I decided, let's do I to the sixth. Let's take I to the sixth. Well, that's going to equal, you could take that 6 divided by 4. Well, 4 goes into 6 how many times? It goes in 1 time, but you'll have a remainder of 2. It's this remainder of 2 you want to focus on. That's going to be the same as I squared, which would end up giving you negative 1. All right, let's do I to the seventh. I to the seventh, well, that you take that 7, divide it by 4. 4 does go into 7 one time, but you have a remainder of 3. It's that remainder of 3 you want to focus on. So I to the seventh is the same as I to the third, which would end up giving you negative I. And then you're going to end up having, let's do I to the eighth. I to the eighth, well, okay. So let's take 8 and divide it by 4. 8 and divide it by 4, you get exactly 2 with no remainder. Again, it's that no remainder. This is the same as I to the 0, which is also the same as I to the fourth, if you notice. You get 1. So I breaks down into cycles of 4. For every 4, it just cycles back around. So let's say I do I to the 100th power. Well, let's take that 100 divided by 4. What's 100 divided by 4? That's exactly 250 with no remainder. 250 with no remainder, that's the same as I to the 0, which would just give you 1. So I to the 100th would just equal 1 because you have no remainder. So when you start getting above 4, you divide by 4 and you only care about what your remainder is. That'll dictate which form of these it takes. Alright, so having done all that, you can also multiply and divide imaginary numbers. So let's say I have negative 5i plus I squared. We want to write this in standard form. Now all of a sudden it's negative 5i plus I squared. Well, what is I squared? That's negative 1, right? So this will become negative 5i minus 1, which in standard form you would actually take negative 1 minus 5i. So in standard form, negative 5i plus I squared is negative 1 minus 5i. All right, let's see. Now I'm going to take negative 3i squared plus I. If I take negative 3i squared plus I, well, all right, that I squared is the same as negative 1, so this would be negative 3 times negative 1 plus I, which would just turn into 3 plus I. So in standard form, negative 3i squared plus I just turns into 3 plus I. Now you can also add and subtract whole complex numbers. Let's say you have 4 plus I quantity minus 7 minus 2i. So you can add and subtract whole complex numbers. It's really no different than doing a variable. What you would end up getting is 4 plus I minus 7 plus 2i. So in standard form, this would end up becoming negative 3 plus 3i. You always want to write your result in standard form. So you would get negative 3 plus 3i. Let's see, we have 11 minus 2i minus negative 3 plus 6i. So here's the difference of two complex numbers. You have 11 minus 2i quantity minus the quantity of negative 3 plus 6i. So this would turn into 11 minus 2i plus 3 minus 6i, which now you just add like terms like you would adding and subtracting variable equations. You end up getting 14 minus 8i. So in standard form, you would end up getting 14 minus 8i. All right, now how about this one? You have 7 plus the square root of negative 18 plus the quantity of 3 plus the square root of negative 32. So how the heck are we going to deal with that? Well, let's break these down in brackets here. So let's deal with the 7 plus the square root of 18. That's literally the same as 7 plus the quantity of I, because the square root of negative 1 is I, times the square root of 9 times the square root of 2. And then let's deal now with the second quantity, plus, you'll have that 3 plus in parentheses. Well, square root of 32 is definitely I times the square root of 16 times the square root of 2, which now we'll simplify a little bit further. So this would all turn into 7 plus, all right, so square root of 9 is 3, so this would be 7 plus 3i times the square root of 2, plus, you'll have 3 plus, now square root of 16, that's 4, so 3 plus 4i times the square root of 2, which when you add all these together and collect like terms, you end up getting 10 plus 7i times the square root of 2. And that would be the answer in standard form. You would end up getting 10 plus 7i times the square root of 2. Let's see if we could do one more like that, then we'll move on. How about this one? -1 plus the square root of -8 plus, we have 8 minus the square root of -50. That one looks like a doozy. So -1 plus the square root of -8 quantity plus the quantity of 8 minus the square root of -50. Okay. Well, let's break down each of these quantities here. So let's set up our brackets. So you'll have the first quantity, -1 plus, in parentheses, square root of -1 times the square root of 8. So that turns into I times the square root of 4 times the square root of 2. Alright, so there's your first quantity broke down. Plus, now let's deal with your second quantity. So you'll have 8 minus, in parentheses, square root of 50 is definitely I times the square root of 50, which will break down into I times the square root of 25 times the square root of 2. Alright, let's continue further. So this would break down into -1 plus, now, okay, square root of 4 is 2, so this would be plus 2i times the square root of 2. All this plus the quantity of 8 minus, alright, so the square root of 25 is 5, so this would be minus 5i times the square root of 2. So now we have this broke down into some imaginary forms, which now we're just going to add like terms. -1 plus 8 is 7, and then 2i times the square root of 2 minus 5i times the square root of 2. This would be minus 3i times the square root of 2. So in standard form, this would become 7 minus 3i times the square root of 2. Alright, so that's adding and subtracting them. We can also multiply them. Let me get a different black marker here. Alright, so let's see here. Now, when we go to multiply, let's say you have the square root of -6 times the square root of -2. A lot of people make this mistake. They think, and it's not the same thing as taking the square root of -6 times the square root of -2. They would think you just get the square root of +12. That's not quite how it works. Not with imaginary numbers. Alright, so it's important to understand what exactly is going on here. So let's break this down. Let's take your first one, the square root of -6. Well, that's the same as I times the square root of 6 times I times the square root of 2, which this is going to end up then giving you I squared times the square root of 12. Alright, so what is I squared? That's the same as negative square root of 12, but we want to get this in simplest form. Square root of 12 breaks down into the square root of 4 times the square root of 3. So this would end up becoming 2i. No, this would end up becoming, there is no I. It would just be negative square root of 4 times square root of 3. So it would end up becoming -2 times the square root of 3. So you actually end up getting a negative answer. This would end up being negative 2 times the square root of 3. Alright, another one like it. We have the square root of negative 5 times the square root of negative 10. Well, again, let's look at what's really going on with these two quantities. So, square root of 5 is the same as I times the square root of 5 times, then you have I times the square root of 10, which would really turn this into I squared times the square root of 50. Well, I squared is negative 1, right? So this would end up being negative of the square root of 50. Well, what's the square root of 50? That's the square root of 25 times 2. This would just end up becoming negative 5 times the square root of 2. So the square root of negative 5 times the square root of negative 10 becomes negative 5 times the square root of 2. So now you're beginning to see how imaginary numbers can have ramifications in the set of real numbers. That's why together they're called the complex numbers. All right. Let's say now we're going to do a foiling one. So we have 1 plus I times the quantity of 3 minus 2i. Alright, so we have 1 plus I quantity times the quantity of 3 minus 2i. Well, treat this like you would any algebraic quantities and FOIL it. So 1 times 3 is 3. Then you'll have minus 2i plus 3i. Then this will become minus 2i squared. Well, we were good up until the I squared, because what is I squared? That's negative 1, right? So this will become 3 minus 2i plus 3i minus 2 times negative 1. So what does that become? That becomes 3 minus 2i plus 3i plus 2. Now we can just write this in standard form. This would just turn into 5 plus I. So the number you get in standard form would end up being 5 plus I. This is why it's important to understand the cycles of I. Alright, let's do this one. 6 minus 2i quantity times 2 minus 3i quantity. Alright, well, again, we'll FOIL. 6 times 2 is 12. Then you'll have minus 18i minus 4i plus 6i squared. So we were good till we got to 6i squared, because what's I squared? That's actually negative 1. So this will become 12 minus 18i minus 4i plus 6 times negative 1, which would turn this into 12 minus 18i minus 4i minus 6, which now we can get a number in standard form. This would turn into 6 minus 22i. So the number we're looking for in standard form is 6 minus 22i. And of course we can use the distributive property with these too. Let's say we have 4i times the quantity of 8 plus 5i. Well, you can use the distributive property, which would end up giving you 32i plus 20i squared. I we can't do anything with, but that I squared becomes what? Negative 1. So this would turn into 32i plus 20 times negative 1, which in standard form would turn this into negative 20 plus 32i. So this in standard form is negative 20 plus 32i. And let's do one harder one. All right, so we have the quantity of 4 plus 5i to the second power minus the quantity of 4 minus 5i raised to the second power. So we got two quantities we're subtracting, but they're both to the second power. So let's see what's going to happen here. Let's deal with your first quantity. That's going to turn into 16 plus 40i plus 25i squared. All that minus your second quantity to the second power. This would end up being 16 minus 40i plus 25i to the second power. Which now we can just go through and distribute the negative sign. You end up getting 16 plus 40i plus 25i squared minus 16 plus 40i minus 25i squared. Well, here's some good news, or maybe not. Well, 16 minus 16 is 0. Then we have 40i plus 40i, that's 80i. And then 25i squared minus 25i squared, that's 0. So literally, you'll just end up getting an answer of 80i. By the time you simplify, it's just 80i. So you can treat these largely like you would any variable equation. It's just you're dealing with I, the square root of negative 1. Okay. Now, when we talk about imaginary numbers, they occur in conjugate pairs. So you have a plus bi for the standard form of a complex number. They always occur in conjugates. So the conjugate of a plus bi is a minus bi. So you would take that a and then you would minus the bi. So when would you use the conjugate of a complex number? Whenever you're doing division. So let's say, for example, you have something like 6 over I. You have 6 divided by I. Just like it's true for radicals with real numbers, it's the same with imaginary numbers. You want to rationalize your denominator. In order to do that, you have to multiply by the complex conjugate. Now, a lot of people make this mistake, think, oh, I can just multiply everything by I. No, that's actually not how that works. What is I the same as? In complex form, full complex form, it's 0 plus I, right? That's the normal way it really would be in complex form. What's the conjugate? The conjugate would actually be 0 minus I. The conjugate of I is actually then, it would just simplify into negative I. So it's very important you understand the standard form of a complex number. So let's try that 6 divided by I again. If we understand that I is the same as 0 plus I, that means we need to multiply both numerator and denominator by 0 minus I, or simply negative I, in order to rationalize the denominator. So go through and multiply, you'll get negative 6i over negative I squared. Well, what is I squared? That's negative 1, so this would give you negative 6i over the negative of negative 1, or simply just negative 6i. So in simplest form, this would end up being negative 6i. And I got plenty more where that came from. Let's say we have negative 5 over 2i. All right, well, what have we got to understand about 2i? In true complex form, isn't that the same as 0 plus 2i? So in order to rationalize, we would need to multiply the numerator and denominator by the complex conjugate, which would be 0 minus 2i, or simply just negative 2i for both numerator and denominator. So this is going to turn into 10i over negative 4i squared. Well, what is I squared? That's negative 1. So this would turn into 10i over negative 4 times negative 1, which would turn into 10i over 4, which in simplest form would just end up being 5 over 2 times I. So this would turn into 5 halves I. A little bit harder one. We have 2 over 4 minus 5i. So we've been given 2 over 4 minus 5i. Well, we want to rationalize the denominator, so we have to multiply the numerator and denominator by its complex conjugate, which would be 4 plus 5i. So multiply both numerator and denominator by that 4 plus 5i, which is going to end up then giving you in the numerator 8 plus 10i divided by, this is just, this will turn into a perfect square binomial. This would be over 16 minus 25i squared, which we can simplify further. You'll end up getting 8 plus 10i over 16 minus 25 times negative 1, which would really give you 8 plus 10i over 16 plus 25, which would end up giving you 8 plus 10i over 41. That's one way you could write it, or you could write it as 8 over 41 plus 10 over 41i. This is really the correct way to write it in standard form. It would be 8 over 41 plus 10 over 41i. All right, let's see here. Let's do 3 over 1 minus I. So we have 3 over 1 minus I. Well, we're going to have to rationalize the denominator again, so you have to multiply by the complex conjugate. So that would be 1 plus I. So take the numerator and denominator, multiply by 1 plus I, which would simplify into 3 plus 3i. Then you just do the foiling. This would turn into a perfect square binomial. This would be 1 minus I squared, which would turn into 3 plus 3i over 1 minus negative 1, which would end up giving you 3 plus 3i over 1 plus 1. So this would be 3 plus 3i over 2, which to write in standard form, you got to separate these. You would end up getting 3 halves plus 3 halves I. So the number you should get in standard form would end up being 3/2 plus 3/2 I. All right. Let's see. We have 2 plus I all over 2 minus I. Well, you want to rationalize your denominator, so go ahead now and multiply both numerator and denominator by your complex conjugate, which would be 2 plus I. So this is going to turn into 4 plus 2i plus 2i plus I squared all over 4 minus I squared, which would simplify into 4 plus 4i minus 1 all over 4 minus negative 1, which would end up becoming 3 plus 4i all over 4 plus 1, which would end up giving you 3 plus 4i over 5, but we have to write this in standard form, so you would end up getting 3/5 plus 4/5 I. In standard form, you end up getting 3/5 plus 4/5 I. All right, and then let's say you had something like this. So you'll have I over the quantity of 4 minus 5i to the second. This is actually a pretty loaded problem because we're going to have to deal with expanding the denominator to the second power before we even have a prayer of simplifying this. So this would turn into I all over 16 minus 40i plus 25i squared, which is going to simplify into I all over 16 minus 40i minus 25, which would turn this into I over negative 9 minus 40i. So here's really what we're up against. We're up against I over negative 9 minus 40i. Now we can go ahead and rationalize the denominator by multiplying the numerator and denominator by its complex conjugate. Well, the complex conjugate of negative 9 minus 40i is negative 9 plus 40i. So this would be times negative 9 plus 40i all over negative 9 plus 40i. So this would end up becoming, if you simplify the numerator, you would get negative 9i plus 40i squared all over 81 minus 1600 I squared. That looks pretty hideous. Well, what's this going to turn into? In the numerator, this would end up turning into negative 9i minus 40 all over 81 minus 1600 times that negative 1. So now you would have in the numerator negative 40 minus 9i all over 1681. And I'm pretty sure it doesn't simplify any. I don't think 1681 and 9 factor at all, but I just want to rule that out real quick. Okay, good. That's safe. Let's see. So 1681 divided by 9. Nope. Nope, they don't simplify at all. So in standard form, your answer is going to end up being negative 40 over 1,681 minus 9 over 1,681 times I. That's the number you get in standard form. So that one was a bit of a doozy, but that's exactly what it would be. All right. And you can also add fractions with I. So let's say you have something like 2 over 1 plus I minus 3 over 1 minus I. So now we have two fractions, both have imaginary numbers in the, or complex numbers rather, in the denominator. The end goal is still the same. Let's get a common denominator. So the common denominator, of course, would be 1 plus I times 1 minus I. So this would end up turning into 2 times 1 minus I minus 3 times 1 plus I all over 1 plus I times 1 minus I. Now you have the same common denominator. Let's go ahead and simplify this. So in the numerator, you would get 2 minus 2I minus 3 minus 3I all over 1 minus I squared, which would be the same in the numerator as negative 1 minus 5I all over 1 minus negative 1, which would turn into negative 1 minus 5I all over 1 plus 1, which would simplify into negative 1/2 minus 5/2 I. So you'll end up getting negative 1/2 minus 5/2 I. All right. So let's see, we have 2I over 2 plus I plus 5 all over 2 minus I. Well, again, the goal, we want to get the same common denominator, so your common denominator will be 2 plus I times 2 minus I. So this will turn into 2I times 2 minus I plus 5 times 2 plus I all over 2 plus I times 2 minus I, which when we simplify the numerator will become 4I minus 2I squared plus 10 plus 5I. All that all over your denominator of 4 minus I squared. So let's see, in the numerator this would simplify into 10 minus 2 times that I squared, which is negative 1, plus 9I all over 4 minus negative 1. So let's see, 10 plus 2 is 12. This would end up turning into 12 plus 9I all over 4 plus 1, which we know is over 5. So your final answer should end up being 12/5 plus 9/5 I. So your final answer would end up being 12/5 plus 9/5 I. All right. Let's do one more with fractions here. So let's say we have I over 3 minus 2I plus 2I all over, wow, 3 plus 8I. So not as nice of fractions to work with, but we can still very much work with it. So I over 3 minus 2I plus 2I over 3 plus 8I. Still, we want the same common denominator. So this is going to end up turning into I times 3 plus 8I plus 2I times 3 minus 2I all over the quantity of 3 minus 2I times the quantity of 3 plus 8I. Yep, we're in for a real doozy. So simplify the numerator, you get 3I plus 8I squared plus 6I minus 4I squared all over, let's FOIL the denominator, you would end up getting 9 plus 24I minus 6I minus 16I squared. Alright, so now this is going to simplify in the numerator of 9I plus 4I squared all over 9 plus 18I minus 16I squared. Alright, well, in each the numerator and denominator we have to deal with the I squareds, don't we? So this would turn into 9I minus 4 over 9 plus 18I plus 16, which now we simplify it and put each in standard form, you end up getting negative 4 plus 9I over 25 plus 18I. It would look like we're done, but we're not. We still have to rationalize the denominator and write this as an imaginary number in standard form. So now we have to multiply numerator and denominator by the complex conjugate, which in this case would end up being 25 minus 18I. So let's multiply each by the complex conjugate, which now we'll just FOIL each numerator and denominator. Numerator, you get negative 100 plus 72I plus 225I minus, boy oh boy, I gotta take 18 times 9. I think I know what it is, but I want to be sure. Yep, minus 162I squared all over 625 minus 324I squared. Yowzer. So this will simplify further into negative 100. All right, 225 plus 72, that would end up being 297I plus 162 all over 625 plus 324. So this is going to simplify in the numerator into 62 plus 297i all over 949. Well, let's see if somehow, by some miracle, any of these break down at all. I don't think they do, so we're looking at the truly awful 62 over 949 plus 297 over 949i. That would be your final answer in simplest form. 62 over 949 plus 297 over 949i. All right, let's do a bit more simplification with higher powers of I. Let's see here. Let's do negative 6i to the third plus I squared. So we want to write this again as a complex number in simplest form. This time you have negative 6i to the third plus I squared. Well, a couple things then. What's I to the third? That's just negative I, right? So you'd have negative 6 times negative I. Now what is I squared? That's negative 1, so this would be minus 1. So in standard form, this would just become negative 1 plus 6i. So in standard form, it's simply going to be negative 1 plus 6i. This is why understanding the cycles of I is very important. All right, 4i squared minus 2i to the third. So we have 4i squared minus 2i to the third. Well, what's this going to turn into? So, a couple things. I squared is negative 1, right? So this would turn into 4 times negative 1 minus 2 times what is I to the third? That's just simply negative I. So this would end up turning into negative 4 plus 2i. That would be the standard form and simplest form of this complex number would be negative 4 plus 2i. All right, now what if they gave you something like this? The square root of negative 75 raised to the third power. All right, well, a couple things here. The square root of 75, the square root of negative 75 breaks down into I times the square root of 75, which would be raised to the third power. Well, what is I to the third power? That's just negative I, so you'd end up getting negative I. Now the square root of 75, let's keep that square root of 75 to the third. Well, that would just end up being times 75 times the square root of 75. So this would end up then turning into negative 75i times, now what's the square root of 75? That's the same as the square root of 25 times the square root of 3, right? All right, so what is square root of 25? That's just 5. So let's take 75 times 5. you end up getting negative 375. So this would simplify into negative 375i times the square root of 3. And that would be the best you could do. It would turn into negative 375i times the square root of 3. All right, now we have the square root of negative 2 raised to the 6th power. So, square root of negative 2 raised to the 6th power. Well, what's that the same as? This is going to be the same as I times the square root of 2 raised to the 6th power. So let's separate these. This is the same as I to the 6th power times the square root of 2 raised to the 6th power. Now, what is I to the 6th power? It's greater than 4, right? So let's take 6 divided by 4. 4 goes into 6 one time, but you have a remainder of 2. It's that remainder of 2 that matters. So this would be the same as I squared times, now what is the square root of 2? Is that not the same thing as 2 to the 1/2? So take 2 to the 1/2 raised to the 6th power. Well, this is going to end up then turning into, what is I squared? That's just negative 1 times 2 to the 1/2 to the 6th. That's the same as 2 to the 3rd. Or this would simply just end up being negative 8. So the answer you should get for this would end up being negative 8. All right, we have a couple fraction ones with higher powers of I. And then we're going to do a little bit of graphing. So let's say you're given 1 over I to the 3rd. You have 1 divided by I to the 3rd. Well, what is I to the 3rd? That's just negative I, right? This is going to be the same as 1 over negative I. Now, as a complex number, isn't negative I the same as 0 minus I? So you're going to have to multiply the numerator and denominator by a complex conjugate, which would be 0 plus I, or just simply I. So multiply the numerator and denominator by I. What you'll get is I over negative I squared, which would end up being I over the negative of negative 1, which would be I over 1, or simply I. So 1 over I to the 3rd just converts into I. All right. One more like it. We have 1 over 2i, that quantity raised to the 3rd power. Well, let's expand the denominator. This is the same as 1 over 8i to the 3rd. Well, what is I to the 3rd? That's the same as negative 8i, right? So this would be the same as 1 over negative 8i. Now, what is negative 8i in its full standard form of a complex number? That's 0 minus 8i. So you'd have to multiply by the conjugate of 0 plus 8i, or simply 8i. So you would have 8i over 8i, which you're multiplying it by, which would convert into 8i over negative 64i squared, which would turn into 8i over negative 64 times negative 1, which would turn into 8i over 64, which would just give you 1/8 I. So in simplest standard form, this would convert into 1/8 I. All right, let's do a little bit of graphing here. We're going to graph 6 numbers in the complex plane. So we can actually plot numbers in the complex plane. Let me show you that real quick. Come on. There we go. Had to get my fingers to cooperate with these magnets. They're good magnets, but man, are they tight sometimes. All right, I think I got it now. Perfect. 2 more panels. I think I'll just take it one at a time this time. All right, so you can also plot numbers in the complex plane. The complex plane works very similarly to your regular XY coordinate plane. The difference is what would normally be your x-axis, this is the real axis. So this is the real axis here. What would be your y-axis, your x-axis? Your y-axis is your imaginary axis. So you have your real axis, which would act as your x-axis, and then your y-axis acts as your imaginary axis. So if we go to plot, let's just plot -6 in the set of complex numbers. The standard form is what? That's the same thing in standard form of a complex number as -6 plus 0i. So that tells us first, you're going to want to go -6 in the real direction. So 1, 2, 3, 4, 5, 6. And then 0 in the imaginary direction. So it would pretty much be similar to -6, 0 in the set of real numbers, but you're actually going -6 on the real axis and up or down 0 on the imaginary. So right there you would have plotted -6. So when you plot complex numbers, instead of using commas, they use plus or minus. It accomplishes the same thing, but in complex numbers, that's how you do it. All right. Let's say I'm plotting 1. I just plot 1 in the complex field. Well, that's the same as 1 plus 0i, right? So that tells me I'm going to go over 1 positive in the real numbers, but up or down 0 in the imaginary. So right here is 1, literally 0.1. Now, let's change this a bit. Let's say I'm going to plot -5i. I'm just given an imaginary number to plot. Isn't that the same thing as saying 0 minus 5i for the full form of the standard complex number? So this time I'm going 0 on the real, but I'm going down 5 on the imaginary. So -5i would be down here. There's my -5i. Now let's say I do +3i. I'm going to plot +3i. Isn't that the same thing in standard form as 0 plus 3i? So this is going to tell me I'm going 0 in the real axis. I'm not moving it all left or right, but I'm going to go up 3 on the imaginary. So this is my 3i right there. Now where it gets interesting, we have only 2 of these ones coming up. Let's say you had something like 4 minus 5i. That's almost comparable to 4 comma -5 in the real numbers, but 4 minus 5i, so this tells me I'm going over 4 positive in the reals. So 1, 2, 3, 4. And then I'm going to go down 5 on the imaginary, so 1, 2, 3, 4, 5. Right there. I plot my point. That is 4 minus 5i, right there. So I would be in the fourth quadrant on the complex plane. 4 minus 5i is right there. And then we have just one more. Then we're done. Let's say I give you -7 plus 2i. So we got -7 plus 2i. We want to plot that in the complex plane. So this tells me first for the standard form, I'm going left on the real axis by 7 units. So 1, 2, 3, 4, 5, 6, 7. And then up 2 on the imaginary. So 1, 2. So that would be right here. That is my -7 plus 2i right here. I end up in the second quadrant. So plotting complex numbers is really pretty simple. So that's it for this lesson. Next lesson we will get into the fundamental theorem of algebra, which will involve solutions to polynomials that involve the whole set of complex numbers. We will no longer just be restricted to the reals. We will also have the whole complex set of numbers for solutions. So I hope everyone has a great day. Take care.